Hello, everyone. Welcome to our third talk of the day. Our speaker now is Hannes Stärk, explaining us the topic of generative models for biomolecular prediction, dynamics, and design. Thanks University of São Paulo and the Institute of Mathematical and Computer Science for the help in promoting this event. And a special thanks to Hannes Stärk. Thanks for accepting our invitation. Hannes is in the third year of PhD student at MIT, working with Regina Barzilay and Tommi Jaakkola on generative models for biomolecules. Okay, you're good to go, Hannes.
Okay, then is my screen already being shared? Because I have like a stop screen now. That looks pretty good. Then I would say we get to some slides.
Very good.
Okay, then I'll just go ahead. And yeah, as already mentioned, right, we are talking about generative models for biomolecules today, and I'll split this into these three areas of prediction, dynamics, and design. And the thing is, right, when people engineer their molecules and we want to like decide how should we change our molecule or how should we change our protein such that it has certain properties that we're interested in, like for example, it is a small molecule that binds to a protein that is part of a virus and thus it inhibits the function of this protein of the virus and the whole virus no longer functions, and then we have a drug against this virus. Right, when designing such small molecules or when designing proteins that fulfill similar tools or do similar functions, like functioning as a drug, for example, or we design enzyme proteins that can catalyze reactions that are important in industry for making textiles, things like that. When doing such engineering tasks for biomolecules, then it's now often the case, or there has been a lot of success in not modeling molecules and proteins from first principles, and for example, simulating them based on these first principles of how atoms move, of how where some electron density of our atoms is, but by rather turning to machine learning and collecting data of inputs and outputs, and then just learning a function of machine learning to predict the outputs from the inputs. And yeah, one example that is now very prominent for this is, of course, structure prediction of proteins and what's called AlphaFold for doing that. AlphaFold was maybe the most successful first tool using machine learning for doing this, right? And here the task is you have these proteins which are made up out of a sequence of amino acids where there are 20 possible amino acids. So these amino acids are just molecules, and there are 20 different types of these molecules. And then you have a sequence of them, like these molecules are often represented as these letters here. And now you just have a sequence of these molecules of arbitrary length, and you want to predict what structure does this specified molecule fold up into. Right? You have the sequence of molecules that gives rise to a larger molecule, and because it's made up out of these 20 specific molecules, which are called amino acids, we call the thing a protein. So this is a protein sequence, and now the prediction task is predicting the 3D structure into which these proteins fold up into. And this was done, for example, with AlphaFold, for which this week on Tuesday, I believe, no, last week on Tuesday, I believe, something like that, the Nobel Prize was awarded for to Demis Hassabis and John Jumper for advancing protein structure prediction with machine learning and by building tools such as this that do this task of taking as input a protein sequence and then predicting the 3D structure into which this folds up to. And if you now, during this talk, have any questions about the biology aspect, about the ML aspects, then please send them into the chat. Our moderator will relay them to me and interrupt me, and we can address them right away. Okay, but today we're interested in cases where the target of our function, or yeah, the target is a distribution. So cases that call for generative models. Like we have one input that we're maybe the sequence, the generative model is conditioned on, and what we want to produce is a whole distribution of possible outputs. Like for example, if we now already talked about the protein case, then this distribution could be the distribution of possible structures that the protein could take on, instead of predicting just one structure, because there's actually a whole, like proteins are a flexible object, right? The molecules are a flexible object, and there could be multiple structures that they can take on, and each structure has a different probability, so we have a distribution over these structures, and we would want to sample this. And this would be one case of a where a generative model would be valuable for this biomolecular task. But concretely, we'll be splitting this direction today into three, or this task or this direction of generative models for biology into three directions of prediction. So here the first one, and we'll be talking about three applications and three papers for this as well. And for prediction, we say that, right, it's a little weird. Like, why would you want a generative model for a prediction task? And the reason that we argue there is that if you have a prediction task that is so hard that you have a lot of uncertainty, then this predictive uncertainty will give rise to a distribution, and your task attains a distributional nature. And the example that we'll be looking at for that is molecular docking. So where we're trying to predict the 3D structure of how a small molecule, or in which a small molecule binds to a protein structure. Then for the second direction that we think generative models can be valuable for biomolecules, we'll be looking at design tasks. So inverse problems where we have one input, like one desired property, and then there are many solutions that would achieve this desired property. And we then want to generate all these possible solutions with a generative model. And the example for this task will be a DNA sequence design. So when you want to design some DNA sequences that satisfy certain properties that we're interested in. And then thirdly, we're looking at cases where you actually have the quantity of interest itself is actually a distribution. So the dynamics, or the ensemble of structures that a protein can take on, for example. And for that, we'll be looking at a model that we recently built for generating molecular dynamics trajectories. And of course, this work was done with many close collaborators here, especially with Bo and Jing was involved in all of this, and Tommi, Jaakkola, our joint advisor. And yeah, Regina, Barzilay, Bonnie Berger, and Tommi are our advisors. And the other co-authors besides Bon on these works are Gabriele and Chen Yu. Okay, but then let's get to it. And well, before we actually get to our three application areas, I will give some background on diffusion models, or some background on the generative models that we will then use for addressing each one of these tasks. Because we have a little three-step recipe for building generative models, or for building generative models in general, and we will apply these to or this three-step process for building a generative model, we will apply it to each of these three directions. Okay, and as I said already, the generative model that we'll be using, it will be a diffusion model or a flow model, which you can call it as well. And why a diffusion model? Well, for one, we know that diffusion models can produce very high quality samples. If you've maybe seen online some generated images of diffusion models, or text to image diffusion models. And what's maybe more relevant for us now, or more specialized to us, is that diffusion models and flow models are very flexible in the types of data modalities that you can handle with them. And with proteins or biomolecules, you have many different data modalities like continuous protein coordinates or the discrete a discrete protein sequence or data on manifolds like the torsion angles of a small molecule. And oftentimes you even have joint data where all these modalities come together. And with flow models, we'll be able to tackle each of those. And for every one of these scenarios here or types of data, we will actually build a flow model in this talk. Okay, but then what is this? What is our three-step process for building a generative model? Well, on a very high level, step number one is we have some data and we need to come up with a process to turn this data into noise. And this process, then we also need to be able to sample along it. So we need to be able to sample like half noised images, for example, half noisy data points. And then the reason that we need to be able to turn it into noise is such that then later during inference, we can sample something from pure noise. And yeah, maybe we then have a way to turn this pure noise into data. Okay, but step number one, define a noising process that adds noise to our data points. Then step number two is that we train a neural network that takes a noisy sample as input. Here it is XT, so it takes a noisy data point as input and then tries to predict the clean data which this noise came from. And then step number three is that after we've now trained such a vector field that takes noisy data and predicts us the clean data, then we integrate this by you start from complete noise, put it into the vector field, which points to some clean data point, and then you step a little bit into that direction. And then you have a little less noisy point. You put it into your vector field again, and your vector field now predicts you a different type of clean data. And you go into that direction again, and you follow it. And yeah, then you roll out this whole procedure until the end and obtain samples that hopefully are close to the data distribution that you trained your vector field, your diffusion model, your flow model on. Okay, but this is the three-step process. And when we will now be looking at this or carrying out this three-step process for three applications, we will also encounter some more interesting aspects or some aspects that make this process more interesting, like having a noising process that's defined on a manifold, or having some different objectives that make or that are particularly amenable for our type of data for training this vector field, or integrating this learned vector field with some additional control that then forces our outputs to do or to belong to the categories that we want or to have the desired properties that we're interested in. Okay, but then let's get to it. Application number one, prediction and diffdoc. So what concretely is the prediction task that we're considering here? It is that as input, we're given the 3D structure of a protein and the 2D molecular graph of a small molecule. And what we want to predict are the 3D coordinates of the molecule, of every single atom of the molecule with respect to the protein structure. Right? So your protein structure is given by a bunch of 3D coordinates, of which here in this figure we're only showing the surface, and our small molecule, we as input we only have the 2D molecular graph, and what we want to predict are literally the 3D coordinates of every single atom that the small molecule will take on if it interacts with the protein. Like where will the small molecule stick to the protein? And like this is a very important task for drug discovery. For example, if we want to find a small molecule or we want to reason about how a small molecule interacts with a protein to maybe find out if it inhibits the function of the protein or if it binds to the protein at all. And yeah, they're attaining this or figuring out this 3D structure is important. And then the reason, let me go step back a little bit, right? So Of course, this is also a distributional task in its nature already, because there's actually a distribution of 3D structures that the small molecule could take on. But this distribution is actually very narrow, and most of the distributional nature of this task will arise from the uncertainty of the model that it will have in its prediction. And this is basically where we argue that you should use a generative model for prediction tasks. So cases where the prediction task is so hard that any method for it will have high uncertainty. So any method will have a predictive posterior where the support is either very wide, or it will have a very wide predictive posterior, or even a multimodal predictive posterior. And for here, in our example, in our case, for example, you can imagine this sort of landscape of the predictive posterior of where the model thinks there's density, or there is likely, there's high likelihood for the correct binding pose to be. And if you now have a regression model that can only make a single prediction, then if you optimize your regression model to minimize its mean square error, for example, and then force it to make a single error minimizing prediction for its predictive posterior, then this might be, or this will be a very bad prediction if your predictive posterior, for example, is multimodal, right? And now we argue that in these cases where you have a hard task and high predictive uncertainty, you shouldn't force your model, your regression model, to make a single deterministic prediction, and rather you should train a generative model that can make multiple stochastic generations and sample this predictive posterior. And then you use a post-processing step to rank these and discriminate between these samples that you drew from the generative model, and then return the best ranking one after the post-processing as your final prediction, or you return a set and a ranked set. Yeah, so this is also very intuitive, right? If you have a very hard prediction task, then don't try to solve it in one shot. Instead, draw multiple samples from your generative model, and then solve the easier task for these samples of discriminating between them and finding out which one is the best of those. Okay, but then let's get to it. We're now maybe convinced that for this prediction task, we want a generative model. Let's build the generative model. Step number one, define the noising process for our 3D molecule, right? We have the 3D structure of a small molecule bound to a protein, and now we want to turn it into noise, this 3D structure. So we could just do this here, where we just add Gaussian noise to our 3D molecule structure. But this way, we turn the molecule that's here in this at the beginning in the binding pocket of this protein, we turn the small molecule structure into all sorts of structures that do not look like molecules, and that no longer are realistic molecule structures. And your generative model then has to learn about these all of these unrealistic possibilities, and for how it would have to denoise them. And yeah, instead of having this generative model that has support over all these, yeah, over all these possible structures, we say instead, let's build a generative model that only has support over a smaller dimensional manifold. And this manifold will be given by only adding noise to the torsion angles of the small molecule and to its position and orientation, so it's like its translation and rotation with respect to the protein. So what are the torsion angles of the small molecule? That means that you keep all the local structures fixed, like the bond lengths and the ring structures, for example, and you only rotate around bonds. And yeah, this way you keep these easy to predict quantities fixed, or these very rigid quantities like the bond lengths, for example, fixed, and you only figure out the hard quantities and only have the model generate the hard quantities like the higher level flexibility in the torsion angles and the position and orientation of the molecule with respect to the protein. So you have this lower dimensional manifold over which you now can formulate a generative process, and this lower dimensional manifold for which we now need to figure out a noising process, right? So we say we only add noise to the position, to the orientation, and to the torsion angles. And these are these types of noise that we will add to them is for the position, it's still just noise from a Gaussian distribution. Like the center of mass of the small molecule will be moved by only by just simply by Gaussian noise. Then to the orientations, we add noise from this analog of a Gaussian distribution in the space of rotations. So the space of rotations that's called SO3. And to the torsion angles, we add noise that is from a Gaussian, but from a Gaussian where if you once go around in your angle 360 degrees, then you add up the density of this Gaussian. Okay, so this is our noising process. Then step number 2, learning our denoising vector fields, right? We now know how to obtain our noisy samples. So we take the noisy samples, put them into our vector field, and have our vector field predict the clean samples from the noisy samples. And the way this will work is that this vector field just takes in the 3D structure of the protein and the 3D structure of the small molecule, and they are joined in the same space, so the neural network can reason about this vector field neural network can reason about the orientation of the molecule with respect to the protein and the distances between the atoms and so on. And then it returns as the prediction, the torsion angles, like an SE3 invariant number for the torsion angles. So a number that, an SE3 invariant quantity for the torsion angles, just a single number, a simple number for every torsion angle, and it returns as three numbers in the form of a vector for the rotations and three numbers for a vector for the translations. And that tells us like how do you have to change the torsion angles, how do you have to change the rotation, and how do you change the translation to obtain the clean data point before adding noise to it. Okay, then step number 3, running inference. Right, so we said that we keep these local structures fixed. So when we run inference, we first need to obtain these local structures in some fashion. And that is done with some classical chemoinformatics tools that can easily predict these local structures like rings and bond lengths up to the level of accuracy that we're interested in this task here. And then step number 2, we randomly initialize the ligand structure with respect to the protein by putting it in a random location around the center of mass of the protein, putting it into a random orientation and random torsion angles. And then we ask our diffusion model n times, where n in our case is 20, like to just update, like we ask it, what is the clean structure? What is the ground truth that this noisy structure that you're seeing here came from? And then we step a little bit into that direction. Not completely, just a little bit. And then we ask the neural network again. And we do this again and again and again until we finally end up with our samples. Um, yeah. Then once we have these samples from our generative model, we said we want to rank them to decide which are the best ones. And this we do with a separate model, which we call confidence model, which is just trained to take as input the outputs of our generative model and then to predict whether or not these outputs are within a certain threshold of the ground truth or not. And then we use this classification score as the confidence score. Okay, and then here is just an animation of what this looks like during inference. Right, we start with these randomly initialized molecules, and then we ask our model again and again, how would these structures be updated, and then obtain our final samples from the generative model. And in this case, they all aggregate around this ground truth structure that is shown in green here. Okay, then we will look at two sets of results for this, where here on the y-axis, we're showing the percentage of correct predictions, so to say, where correct means how many, where correct means whether or not the predicted structure is within 2 angstrom RMSD of the, sorry, is within 2 angstrom RMSD of the um, sorry about that, is within 2 angstrom RMSD of the ground truth. And this is done, or right, we this is done on a test set after we trained on a training set where we have many instances from the protein data bank of proteins with small molecules bound to them. And now at test times we have some unseen proteins and unseen molecules and try to find out, um, can we recapitulate this, the ground truth there. And what we found especially exciting was the performance gaps that we achieved to the ground truth, to the baselines, when evaluating with computationally generated protein structures. So when docking to structures that were given by a computational method and not a ground truth crystal structure. And there, the classical methods struggle a lot because they're quite sensitive to very to slight inaccuracies of the computationally predicted structure. Okay, and then here we just have an example of this point that I was making of having a generative model versus a regression model when where the regression model can only make a single prediction, right? And what I was talking about was the predictive posterior landscape, and that especially there is a problem because that's most often where the distributional nature of a task arises. But here, for visualization purposes, we're now just looking at a case where we have aleatoric uncertainty. So uncertainty that's in the data, because here we have a symmetric complex where there are two correct solutions. Here, both of these two binding spots in green would be correct. And then the regression model that can only make a single prediction to minimize its mean squared error here, it puts its prediction actually in the middle of these. Meanwhile, our generative model is able to sample from the modes of this distribution. Okay, and this actually also holds for like across symmetric complexes. So this is not just a cherry-picked result. This holds across all symmetric complexes for this case. But then we get to our second application, and right, if there are any questions, then please, I hope you relay them to me, and we can get to them right away. But if not, we're getting to our second problem now, where we're trying to do design. We're trying to design DNA sequences, and specifically, we're trying to design enhancer DNA sequences. So what are these enhancer sequences? Well, it's just another DNA sequence, but these are not the DNA sequences that you find in genes that are then get translated to proteins that fulfill certain functions in our bodies, but uh, enhancer DNA sequences are sequences that are not translated and turned into proteins, but they regulate whether or not some genes get translated into proteins by like recruiting some transcription machinery and then starting the translation process of the gene. Yeah, and these enhancers, they have this property that they're most of the time cell type specific. So if you put them in one type of cell, then the gene will be translated. If you put them into any other type of cell, then the gene will not be translated. And this is like a desirable property of these enhancers. And when we, for example, want to design a gene therapy or like some cell-based therapies, then you're interested in, for example, designing enhancers that then make a gene being translated only in a specific type of cell, like maybe a cancer cell, for example. Yeah, and we now want to design these enhancers that are only active in a certain type of cell. So in terms of machine learning, our input is one type of cell, and our output is a sequence that is active in this cell type. Okay, then why do we want a why do we want to build a diffusion model here instead of a language model, right? You've seen all these autoregressive models for discrete sequences that are very good at producing natural language. But here we're saying a flow model. It makes a lot of sense because well, first of all, we do not have a lot of data, and oftentimes we find that for training these large transformer models autoregressively, a lot of training data is necessary. But also, the especially important thing is that this type of guidance, right? If you have a language model, then it's very clear how you can steer it for natural language by just providing a prompt at the beginning. But for flow models or for this biological task, then it's very nice to have a flow model because it provides some additional way to steer the model during inference. And that is what we like now call the secret sauce of conditional generation, that is enabled by flow models or diffusion models because of their iterative process in generating the data, where at every point in the iterative process, the whole data object is updated. And the the way this helps us for conditional generation is because, like previously, if we just have our language model, then we can provide it with an additional input, here this class, and condition it on this. But then at inference time, we sample it conditioned on our desired class, and then either the sample that we obtain fulfills this property or it doesn't. And if it doesn't, then well, we can't do anything about it. But with a flow model, what we can do is we can consider two models. One model that takes in this additional input, this additional conditioning signal, and one model that doesn't. So we'll call these vector fields, or the vector fields of these flow models, now V for the conditional one and V prime for the unconditional one. Then what one can do is to interpolate between these vector fields and not run inference with v or v prime, but you instead always follow the vector field that is given by this sort of formulation. We just add up the original conditional vector field and the unconditional vector field scaled by this lambda, where, right, if this lambda is 0, then you will obtain the prediction from the unconditional model, or the generation from the unconditional model. And if it is 1, then you will obtain the generation from the conditional model. But now, why is this interesting, right? The thing where the magic happens really is when you turn, when you increase this lambda and basically say, I don't want just a conditional generation with lambda equal 1, but I want like a really conditional generation, so to say, like something that absolutely guaranteed um, follows this input and adheres to our conditioning input by setting this lambda to be greater than 1. Right? And this might sound strange at first, but this is really works well. This is what people do in practice, where um, for example, here you see this case of a text-to-image diffusion model that is prompted with a stained glass window of a panda eating bamboo. And if you just do conditional generation without guidance, then you obtain these images here on the left that are, well, some of them contain an image of a panda eating bamboo, but not all of them. And they're also kind of lower quality, right? And this is the other thing, that if you do this guidance and set lambda to be greater than 1, then you do not only ensure that you really get something that adheres to your conditioning input that you wanted, but oftentimes the samples also have much higher quality. And this is really this magic of conditional, or of guidance with diffusion models for conditional generation. Okay, but then let's get to it. Let us try to build a generative model for discrete data that works with, for which we can perform guidance. And the way we do this is by relaxing our discrete data onto a simplex. So, of course, what do I mean with this? Basically, our sequence of discrete data, if we had a vocabulary of 3, right, then it would be relaxed onto this 3 simplex, this 3-dimensional simplex. Of course, in practice, if we're talking about DNA, then K and our vocabulary size will be 4, but for visualization purposes, for this set of slides, we will now always consider three simplices, three-dimensional simplices, right? And then the object that we're dealing with, like we turn our data into a sequence of simplices. What previously was a sequence of letters, we turn into a sequence of simplices, where every letter has a corresponding corner. And then like a point on the simplex that's, for example, in the middle of simplex, and would correspond to a mixture of these data points, of a mixture of all the possible letters. And then let's get to our three-step process. Right? We want to now we have this sequence, or this data defined, right? It's the sequence of simplices, and now we want to add noise to it. So we want to define this noising process. And the noising process that we choose here is one that starts out at like a right, and here only looking at a single simplex. The noising process is one that starts out with all density at our data point, like at the corner that corresponds to the letter that is in our data, and then slowly distributes mass across the simplex until you have mass covering all of the simplex uniformly, and your data or your sample could have come from anywhere. And it turns out that a process that fulfills this property is called a Dirichlet probability path, or a Dirichlet noise. So this Dirichlet distribution, is just a type of distribution that we sample this noise from and add it to our data point. Right? You have the data point, and then you just sample noise from this distribution and add it to the data point. Then this very nicely corresponds to this analogy of having letters, right? And the letter that corresponds to the corner, and then slowly turning them into mixtures of letters, like where at the end each letter is represented, or if you have a completely noisy data point, then you can't distinguish which data point or which letter your data actually came from. Okay, but then we have this this noising process, and then step number two: how do we train this noising model? Well, we take the clean data, we add this Dirichlet noise to it that we just discussed to obtain a noisy sequence, and we put the noisy sequence into a neural network, and the neural network just predicts with a classification loss with cross entropy what is the clean data that this noisy data came from, right? What is the clean data that we added the noise to? And then at inference time, we convert the probabilities that our model predicts for each of the possible letters into a vector, and integrate this vector along on the simplex to along this vector field to obtain a final sample. And here's just a visualization of what this would look like if we had a single simplex where our vector field or our neural network now always predicts this corner and this corner with 60-40 to be like with 60% and with 40% to be the corners that the data came from. Then if we start at, for example, the dark spot, or if we start from this yellow spot, then the paths that these samples would trace out are shown here as at the beginning of integration, then the next step, the next step, and the next step, until we end up somewhere very close to the corners and discretize it, and then turn it into the letter that corresponds to this corner. Or if we had started with the red dot, then it would correspond to this corner. Okay, but then let's get to some experiments for this. And the experiments that we carry out here, for them, we train it. We train our model on two different data sets, which always contain, in one case, 81 different classes, and in the other case, 41 different classes, right? And the thing that we wanted to test out here is, can we generate cell type specific enhancers, right? This was our task. So we have this additional class input to our model, and then we perform classifier guidance with it, and classify free guidance with it, and want to see what we the samples that we obtain. And what we want to see is whether these samples are realistic and whether they actually correspond to a specific cell type, right? So we will have this our generative model that takes some noise as input and then generates us a sequence with this additional cell type conditioning as input. And then we use an additional classifier, just completely separately trained for evaluation, that will tell us how high is the probability for the sequence to actually belong to the cell type that we conditioned on. And we use also the embeddings of this cell type classifier to assess how distributionally correct these sequences, these produced sequences are compared to usual DNA sequences or usual enhancer sequences that you would encounter in nature. And we do that to assess how realistic these sequences are. And then we'll now look at plots like these, where in blue you have this measure of realisticness, which you, or let's call it realism error, which you want to be as low as possible. So lower means that the sequence is more realistic. And in orange, you have the probability of the sequence to actually belong to the class that you specified as input. And here on the x-axis, you see the guidance strength that we supply the model with. So the guidance parameter lambda. So at guidance parameter lambda being equal to 0, you do no guidance. And of course, then there's no reason for why your sequence should be conditioned on your target cell type. And here at lambda equals 1, we're doing like pure guidance. And yeah, we can see the probability increases, but actually the like once you or the point where you actually get sequences that really strongly adhere to your conditioning is at higher values for lambda, here at 6, for example. And it turns out, just like with images, it is also the case here that if we now produce a model that can, for discrete data, that can be guided at inference time, that you obtain sequences that are of much higher quality and not just adhere more strongly to your conditioning if you do this super guidance, the super conditioning. Yeah, and this also holds across in the aggregate. If we just look at generating data from many classes, then the highest quality results on either data set. Here we were just looking at the realisticness on the y-axis, right? We're just looking at the quality, the fidelity of the sequences, and no longer class adherence. We're just looking at how well can we generate sequences in general. And for both of the data sets that we evaluated on, the highest quality sequences are attained at guidance factors that are greater than 1. So where we're not just doing simple conditioning. Okay, but that is it. But
Hannes,
yes,
let me just interrupt you a bit briefly here. We have two question in the chat. Bonfire asked, how did you evaluate the model fitting to the ligand pocket electromagnetic environment? Just by comparing to the crystallographic coordinates?
yes. So we the docking structure evaluation or the binding evaluations that we do here, they are only comparing to the crystal structures. There are some other things that people do, like for example, some other evaluations that we did later on, and some other people did later on of our model, where you look at, for example, the after you relax the structure with some force field, like some molecular dynamics force field, then how close is the relaxed structure to your predicted structure? And there you also want them to be very close. Yeah.
Very good. We have a second question here about the data. Just to recap, what are the data requirements to successfully train generative models for molecules? And are there any limitations related to the availability or quality of the data?
Okay, so I think this question is too broad, right? It depends entirely on the task. If you have a task like docking, then you will need other data, then your data will need to satisfy other properties than if you want to generate DNA sequences. But uh, like for biological data, yes, it very often is the case, or like something general that can be said, yes, it very often is the case that you have like more data scarcity than, for example, for text data or for image data.
Very good. Thank you.
Okay, then we get to a third area where we now want to, um, yeah, well, let's just get into the details. We want to generate an actual distribution, the distribution of molecular dynamics trajectories of a molecule. And this can be basically seen as a video generation task, where now like you have a diffusion model to generate a video, but your video isn't like a usual image type of video, but it is a video of 3D coordinates of how your small molecule moves. And I think it's pretty clear here. You see this animation of 3D coordinates of a molecule in space. And then here you see the first frame of this video, the second, third, and fourth frame. And now the task is to generate such trajectories, such videos of a small molecule. And that means, like, of course, not generate the images literally and generate this video literally. We want to generate the 3D coordinates. For every frame, we want to generate a set of 3D coordinates. Okay, and the way that this was commonly done, and the way that is also done in molecular dynamics, is this autoregressive setup, where you have a small molecule 3D structure, and then you ask your model or your force field of, if you have look at this, then how do you think it will be in the next time step? How do you think it will change? And then you autoregressively predict the next state, the next state, and the next state. And right, this makes a lot of sense with the world being Markovian, right? But if we want to solve a generative modeling task, then in general it can just be that it's better solved if you model this jointly instead of autoregressively, and instead of taking like modeling it in a Markovian way. And so what we do here in our model now is that we have a sequence of noise, and then we use our diffusion model to jointly turn this whole sequence of noisy coordinates into a sequence of the molecular dynamics trajectory. And we just generate a molecular dynamics trajectory jointly instead of doing it step by step. And while this might give us some modeling benefits, the real big benefits that this joint generation gives us is the additional tasks that we can address. Right? Because if we do the step-by-step generation, then the only task that we can address is that we can start with a structure, and then we can predict the future and do some forward simulation. And of course, we can also do this with our model. But with our model, we can additionally do things like you now condition on not just a starting structure, but you condition on a start and an end structure, and then you sample the possible transitions to go between these. Or you do upsampling of a trajectory by having multiple frames and then finding out what are the frames that were between these. Or you do a type of design task where you have the parts of a small molecule at the beginning, and then parts of the small molecule at the end in a different structure, and then you have the model decide or design what is the rest of the small molecule, what does the rest of the small molecule need to be, such that this transition from the start structure to the partial end structure happens. Okay, and for this, the way that we do this is by turning our trajectory of our protein trajectory, or our molecular dynamics trajectory of a protein, into an array of SE3 invariant rototranslation offsets. Um, and these offsets are basically just, yeah, let's get to what these offsets are. But the deal is that once we have these SE3 invariant offsets, right, which no matter how you rotate or translate your input molecule, you will obtain the same tokens. So you're invariant with respect to SE3 changes of your molecule. You're invariant with respect to rototranslations of your inputs, which is something desirable for these types of models to have. Then, if you have this tokenization, then you can just throw the most simple diffusion model framework at these tokens to generate them. And this will just be some adding some Gaussian noise to them and learning how to remove this Gaussian noise. So we will not actually need a three-step process for learning this, for learning to generate this, but it will be very simple, and we won't even go over this three-step process. Okay, but what is this offset tokenization? And the thing is, here in orange, you now see this frame that we condition on, right? In our task setup, we always have like a starting frame that we condition on, a starting frame that we roll out the simulation from. And then these offset tokens, they will be the, like for example, the blue frame here, it will attain the tokens that or the offsets from um, the yeah, it will attain the offsets from the starting small molecule structure. So you have this one small molecule structure, and then after time t, it's a different small molecule structure. And now we just look at the offsets, like instead of looking at the absolute coordinates of the second small molecule structure, we just look at how did the small molecule structure change from your start. And the model can then reason only about these changes. And these changes are then SE3 invariant, these offsets. Okay, but then we just have this, or right, we have now this tokenization, and it's SE3 invariant coordinates, so we can do the same type of diffusion process as we have for images, and it is very simple. And we just have some diffusion or diffusion transformer backbone, where the only change that we introduce is that now we do not just have attention over the data, not just attention over the length of the protein here in our case, but we have an additional attention layer over the time dimension, because we have multiple frames in our video, right? And then we just alternate these two types of attention. Okay, but then let us get to our tasks. And first task being forward simulation. How would we do this? Well, we just have our sequence of noisy frames, turn it into these SE3 equivalent rototranslation offsets, on this tokenization, and we have our conditioning input, right, where we condition on our input frame, and which will just be a single frame if we do forward simulation. And then we put this into our stochastic interpolant framework and generate this trajectory. And if we do interpolation, right, then it will just be two frames that we have as additional input, and that we have as additional conditioning input. And upsampling, just another one. But where it gets interesting is if we do in painting, right? Because then we do not only need to decide how, or like, right, in this task, we then need to decide how does the missing part of the molecule move, but we also need to decide what are the residues that give rise to this movement. And for this purpose, we use this Dirichlet flow matching process that you saw for DNA generation task to also generate the residue types here, to generate the amino acid types that we talked about in the beginning. Yeah, and then we have how we can address these three tasks. And now for evaluations, of course, we also have some quantitative results that you can look at in the paper or that we can talk about afterward. But now I will just get to um, some visual results, some qualitative results, where here, for example, we're doing this task of transition path sampling of interpolation, where we condition on a start state 1 here, that's in this energy landscape of the molecule over here, and a start state in this area 6, where you condition on that molecule structure. And then you sample we want to sample realistic transition paths going between state 6 and state 1. And in this landscape of probability of possible structures that a small molecule can take on that we visualize here, there you can see that the path that our model generates, it goes into the modes with high probability, like the modes where there's actually high density. And we quantitatively also find out that it actually goes into the modes with the right ratios between each of the modes. And yeah, this is just performed, or this sort of transition path sampling we perform after training on a lot of tetrapeptides and then evaluating on an unseen set of tetrapeptides. So peptides or tetrapeptides are proteins where you just have 4 residues, so very small proteins. Okay, and then here the second type of visual result is just you have here the original molecular dynamics trajectory. Yeah, you just have some molecular dynamics trajectory, and then you have here something saved, which you downsampled maybe, and then this is the input to the model, and then this in blue is what our model generated. And of course, you would hope that the small scale motion that our model generates it matches up the dynamics of the original. And in this visualization, you can see that this is the case. And with that, we're drawing it to a conclusion of the 3 areas that we looked at, so the 3 applications for generative models in biology. And the takeaways here might be that for that you also can use, like for the prediction area, it's really literally this insight that it can make sense to use generative models for prediction tasks if the prediction task is so hard that any type of model will have a very high uncertainty that gives rise to a distribution because its predictive posterior will be very wide or have multiple modes. And then the insight for design is that we provided a method to do the same type of controllable generation that you can do for continuous data, and the same type of controllable generation that leads to like really making sure that your model adheres, or your model's generation adheres to your input specification. And we showed how we can also do this for discrete data, and for example, then for designing DNA sequences. And then lastly, maybe a little bit of a far-flung statement, a little bit of more vague, a visionary statement. Video generation is invention, right? We had this case where we try, where we can design a protein, or where we can design a part of a molecule, where we can invent a part of a molecule such that the rest of the molecule does what we want, fulfills the dynamics that we're interested in. Okay, and with that, I want to again thank my co-authors and collaborators on this, especially Bowen, with whom I've worked on all of this, and also our advisors. Okay, then if you have any other questions, then I would be super happy to take them. And besides that, I want to thank the 2 question askers that we already had.
Very good. We have 2 more questions here. One from Samuel. He says, how can generative models accelerate the development of pharmaceutical market today? And what is the level of acceptance of this technology by the healthcare section?
Yeah. So there are, like, for drug development or for therapeutics development, there are many trajectories in which this can happen. Now, looking at our works here, there are maybe 3 that I can highlight. So one is this type of docking, where you screen for small molecules that bind to a particular protein and then are a drug against this protein, which is maybe the target that is important for a certain disease. Then the second is that you design proteins, you design antibodies, for example, that have a very similar function in terms of designing therapeutics. They're just drugs that can inhibit or can interact with the proteins of another virus, for example, or just a protein target for a certain disease, and then interact with this target in the fashion that is needed. And then the third, so we have small molecule designing, small molecule drugs. We have protein binders, protein drugs, like antibodies, for example. And then thirdly, generative models, for example, for DNA sequences, or yeah, for DNA sequences to design cell therapies, to design gene therapies. And yeah, for each of them, I would say the what is the most established probably and the most widely accepted so far, where it's like a most direct translation of what pharma industry has done before to what they can do now, is maybe in docking, like this uh, small molecule protein structure binding affinity prediction. And yeah, there is just a question of how well do these models work, and if you show that they, or if the pharma companies have a lot of success in getting them to work, then they use it. Like if they um, these models actually are accurate enough, then they use it and trust it a lot. This is different from other fields in medicine, right? Where or like medical fields where um, you have some technologies that really work well. Like for example, for breast cancer screening, you have vision models that really work well, but they are not widely adopted just because of regulatory hurdles. In this biospace here, I think it's much more so that we have an extremely hard problem and we haven't solved it well enough yet for pharma industry to be interested in using it. But of course, not be interested in using it is an extreme overstatement. There are good solutions already, and there's a lot of interest in using these generative models for biomolecules from industry, from startups, and yeah, I mean, there's for example Xyra Therapeutics, which received $1 billion funding
Wow.
in its first fundraising round for designing antibodies using protein structure generative models.
Super interesting. Okay, next question. I would like to know if you know any diffusion or multimodal model that allows training on text data, protein sequence, or images, distance maps, and is that a capable and that is capable of generating new sequences.
Okay, so I'm not entirely sure if the question here is about co-generating the protein sequence that is discrete together with a protein structure, for example, or if the question here is about like having a basically text to image generative model where you have the text specification of a protein and then you generate a protein that satisfies um, this text input. So for the text so for the first case where you jointly generate protein structure and protein sequence, yes, that exists. That was developed in our group by Regina, Tommi, Jaakkola, and Andrew Campbell and Jason Yim, some of our co, and it's called multi-flow. Um, and then as for like having a model that basically takes text as input and then produces a protein structure that satisfies this conditioning input, there, no, I don't know of such a model. Like, oh, I think I've seen something like this for just generating sequences, but this, in my opinion, doesn't make sense. So something that actually works. So I think it doesn't make sense because I think text conditioning isn't the right type of input for generating proteins, not the right type of conditioning. And very recently, we developed a model that takes as input like 3D spatial layouts of ellipsoids and then generates your protein that specifies this input. And these layouts, they can then also have some functional annotations like yeah, what type of secondary structure it has, like yeah, what type of function it has.
Very good. Matteo asked, in the DNA diffusion case, a triangular simplex, a square simplex, has some pairs of vertices that are closer to each other if they are in the same edge. Does it
No,
make any practical difference?
so in the there is no such thing as a square simplex. There's a
Mm,
four-dimensional simplex, and this four-dimensional simplex would then be embedded in 3D space. But the and if you look at 3D space, like it then would be a tetrahedron, right? And in this
yeah,
tetrahedron, each edge or each corner is still the same distance apart from each other.
yeah, makes sense. Uh, Janser asked, do graph-based models, graph neural networks, intersect with transformer-based models for the task of generating new molecules for textual prompts?
Yeah, like there's
Uh,
no distinction of like if we talk about intersection of GNNs with transformers, then doesn't matter if we talk about text or whatever data modality. Like a transformer can be seen as a fully connected graph or operating on a fully connected graph, and that's it. And then you basically just have a graph neural network operating, or a transformer as a graph neural network operating on a fully connected graph.
Very good. Do we have more questions? Feel free to ask.
Okay.
Oh, more one. Is there any intention to validate the generative models with experimental spectroscopic methods, infrared, Raman, or biomolecules?
Experimentally validating, yes. With infrared Raman spectroscopy for these applications, the experimental validations that you would do probably do not involve these, do not involve infrared or Raman spectroscopy. But yeah, experimental validation is very important, especially for this second type of task, right? For prediction type of tasks, or for just predicting the 3D structure into which a small molecule binds, you can do some retrospective evaluation where you just look at the ground truth structures, and this gives you a lot of signal. But for if you design some new molecules, then to find out if they actually work, you have to test them. And yeah, there you would then need to do experimental validation. If you generate a new protein or a new drug, does it actually do what you're interested in?
Wonderful, wonderful. Last chance to make a question here.
Okay, then
Just
I will say thank you for the nice questions. And I'll also say thanks for giving me the chance to share these topics here, which I think are pretty interesting, which is why I work on them. And I think there's still a lot of work left to be done. So if someone's interested in that, that is great.
oh, we have a last question here.
Sounds good.
A personal question. Before you started your PhD in this area, did you work in biology, computer science, or at the
Hmm.
intersection of the two?
I was a computer scientist, only worked on computer science, but I was always very interested in natural science, so like biology, chemistry, physics especially. And then, yeah, now I found this space where I can basically work on all these natural science topics that I'm interested in, while also using my expertise in machine learning and having this focus on the one area that I'm maybe the most interested in.
Very good. Hannes, it's a pleasure to have you here. Thank you for accepting our invitation. Um, the Institute and the participants of the event, thank you for your brilliant presentation and content. Uh, we look forward to seeing you in the future. Thank you so much. It was an amazing presentation. Thank you
Cool.
so much.
Enjoy the rest of your sessions and see you around. Bye.
See you. Bye bye. For those watching still, we have more presentations tomorrow, so stay tuned. Um, Tomorrow we have some LLMs presentations, graph neural networks, and reinforcement learning. So stay tuned. Bye bye. See you tomorrow.